So today we're going to be covering Unit 5, and that is 5.1 Fundamental Counting Theorem. Now, before we get into that, I want to talk about independent versus dependent, part of your warm-up, which was that a dependent
variable that represents a velocity that is being manipulated and expanded.
Yes, very well. In short, yes, but in short, a dependent variable does.
That's independent.
Oh, well, does depend. I'm doing dependent first. So dependent variable depends on another.
Independent.
I'm getting there. Hold on. Another set of numerical data, and it is the effect of a given circumstance.
Excuse the interruption. Students, our Marine Corps representatives are here in the office. Please stop by if you'd like to learn more opportunities about the U.S. Marine Corps. Thank you.
All right. Sorry for the interruption. So, now an independent, in contrast, variable, independent variable, does not depend on any other numerical given and is the cause of a given circumstance. There you go. All right. Now, an example of that, just briefly. Okay. For an independent and a dependent. Okay. So an independent example would be temperature. Right? Okay. All right. Just drawing a little thermostat here. Got some mercury in there. There you go. All right. Temperature, right? Okay. So we've got a temperature. And therefore it has it's the cause. It can be manipulated. And it's the x-axis. Okay? All right. The dependent, on the other hand, for example, would be something like test scores. Okay? I know, my terrible drawing skills, even with a straight edge. Okay, so we got some test scores here. I know, I'm just drawing some. Right? Just to give you guys a visual representation. So yeah, test scores. Because they have an effect, they can be measured, and they're on the y-axis. All right, so that's independence, independent variables, all that jazz. Okay, now we're talking about this, or at least bringing this home, because we're going to be talking about sample size basically here in a second. Now, sample size is not the same thing as, sample space. My bad, wrong one. Sample size is what we're talking about when we talk about probability and permutations. Right now, we're talking about sample space. Before we get to that, we got to talk about a principle. Sorry, a principle, and that principle is the counting principle. Okay. Now the goal is to determine the number of ways multiple independent events can occur. So this is the algebraic statement of that. If there is a sequence of independent event, or a sequence of, there is a sequence of an independent event. So put an in there, my bad. An independent event that can occur a sub 1, a sub 2, a sub 3, ... a sub n, meaning that a is the event that's occurring, and the number that's subscript to it is the different type of event, the different types of outcomes, right?
Yeah.
Ways. Then the number of ways all the events can occur is a sub 1 times a sub 2 times a sub 3 times ... times again a sub n. Now what that basically is saying is that if I had, try to get my visual example up, hold on. If I have 2 sets of dice, okay, that means that I have 6 possible outcomes on each one, right? That's 6 events, right? Yeah. On this one, I have also 6 events, which means that I have 2 dice, 6 events each. So I have to multiply them together, and I get a total of 36 possible outcomes. Okay? That's how this works. That's what this sentence is saying, or this part of the statement is saying right here. There's die 1, die 2. If I wanted to add another die, I could. There's die 3. So it would be d sub 1, d sub 2, d sub 3. I'd use d for dice. Duh, I'm lazy. Okay? But do you see how this builds off of itself, right? Great. Now, let's go ahead and switch to the foldable. Okay? Give you a second to write that down. So we're going to move on now to the little foldable here, which basically is going to help explain this even further. Okay, so on the first page right here. Okay? And the way you're supposed to cut it out. Yeah. Okay, so what you're going to do here, all right, is over here, this is now basically just going to drive the point home. The total number of outcomes in a probability experiment is called the sample space. So, for example, if we list the possible outcomes of tossing a coin and rolling a cube, okay, what would they be? Well, here's the thing. If I throw this coin out, just random willy-nilly here, hang on. Okay, I got heads, and I tossed my die. I got 3. So I got heads of 3. Okay, go again. This time I got 2. That time I got tails. Okay, so we got tails of 2. Roll the dice again. Oops. Come on. Up there. There we go. Oof. Now, that sucks. Okay, and I got tails again. So I've got tails and 1. Okay. Roll the die again. Got 6. I got heads. So I got heads of 6. And I think you see where this is going. Right? I think we can pretty much fill in the other outcomes at this point because you can kind of identify the maximum amount, which would be heads of 6 or tails of 6, and the minimum amount, which is tails of 1. Heads of 1, tails of 1, and then everything else in the middle. We got tails of 2. Oops, sorry, heads of 2. My bad. Heads of 2, heads of 3, heads of 4, and heads of 5. We got tails of 3, tails of 4, and tails of 5. Okay, that means we have how many outcomes are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We have 12 outcomes. Okay, this kind of goes back to what I said earlier about having essentially 2 6-sided die. If I have 2 6-sided die, I have how many outcomes? 36. If I had 3 dice, 6-sided die or D6s, how many outcomes would I have? 6 times 6 times 6. So 6 times 6 is 36. 6 times 30. What do you say?
72.
Yes. Wait. No. Hang on. 76. Wouldn't it be 192? No. What is 36 times 6? Hang on. 6, 6, 12. No, 6, 36. Carry the 6, carry the 3. 6, 3. It would be 196. There it is. Okay, 196, I think. All right. Now, why is that important? It's important because in the real world, this adds up quickly. And we're going to talk about that here briefly in a moment. But I want to keep going with this one example with the coin and the D6. Okay? So let's answer this question over here. Using a tree diagram for tossing the coin and rolling the cube. So this is another method of analyzing a sample space. Heads, we can have 1, 2, 3, 4, 5, 6. Okay? For tails, we can have 1, 2, 3, 4, 5, 6. Okay? And therefore you can kind of see the numbers possible, okay? Right, because heads is only 1 and tails is the other one. We just need to look at how many options can combine to them. And that means there's 12 outcomes. Okay? Now, with all of that said, okay? All right, so going on from there, you can use multiplication to find the sample space. This is called the fundamental counting principle. Now the actual phrase comes into play. Meaning we have how many outcomes of a coin? There are 2 outcomes, heads or tails. Dice, a 6-sided dice, which it should say D6 but doesn't, is 6. 2 times 6 is 12. So you don't necessarily need to count out or do a tree diagram or list out all the possible combinations. God, that'd take forever for some of the ones we're about to talk about. You can just figure out, okay, what are the possible maximum number? What's the possible amount of outcomes for that object? And then multiply it by its other neighboring objects. Okay? Case in point. All right, let's take a look now at some other more expanded examples. Tossing a quarter, a dime, and a nickel. Well, all coins have 2 sides. There are 3 of them. 2 times 2 times 2 gives me 8. Rolling 2 dice, assuming they are D6s, that means I'm going to have 6 times 6, which I did this one earlier. That was 36. Selecting a month of the year and a day of the week. Okay, there are 12 months in a year, 7 days in a week, which is going to give me what?
84.
84. Very good. Okay, the number of outfits from 3 sweatshirts, 4 shirts, and 6 pairs of pants. 3 times 4 times 6 gives me 72. Very good. And lastly, making a dessert from the choices in the table below. We have 2 bases, a bowl and a cone. We have 1, 2, 3, 4, 5 colors, flavors of ice cream. Toppings, 1, 2, 3, 4 toppings. Multiply them together, we get, 40. Okay? So again, this isn't too complicated. It's just a matter of determining how much of what possible outcome you have per item. This gets weird when you start wording them tricky, because you can understand, especially when we got done with variations last unit, how the wording can trip you up. So be careful. There's 2 more examples I want to talk about briefly, and then you guys can start working on your classwork. For those at home, you can start working on it as well. It's school, it's Delta Math. But before we get into that, let's talk about these 2 examples real quick. Okay? There are 2 examples I want to talk about. Okay? Now, those being for example, here's one I want to talk about. This is where wording can trip you up. How many ways can students answer a 3-question true or false quiz? So the thing is, there are 3 questions. Each of them are true or false, right? So 3 times 2 would be 3 and 2 each. So, but that's the thing. I just made the mistake. I would say, oh, 3 times 2. No, it's 2 for each question. So it'd be 2 times 2 times 2. If you struggle, go ahead and make a chart of it. Okay, so you have true or false. There's question 1. True or false? True or false? So this is 1 question. This is 2 questions. I always mess up the spacing on these things. Close enough. Okay. Oops. Okay, and that's 3 questions. We have 1, 2, 3, 4, 5, 6, 7, 8. So, or 2 times 2 times 2 equals 8. Okay? So if I asked you, what is the sample space of question 2 or 2 questions, you could just tell me 4. Okay? Does that make sense? Hopefully. The wording can get really weird. So if you're kind of looking at puzzled, it's okay. You'll get this with practice. All right. The other problem I want to look at is how many passwords using 6 digits where the first 2 digits must be letters and the last 4 digits must be numbers. Okay. So we've got a 6-digit code. 1, 2, 3, 4, 5, 6. The first 2 have to be letters. The last 4 have to be numbers. Specifically, digits. And when you hear the word digit, we're not talking about anything past 9. We're talking about 0 to 9. Code language. Okay? So we're looking at 0 through 9. Okay? Now, with that said, how many letters are there in the alphabet? So there's 26 here possible, 26 here possible. And there's 10, 0, you got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so you have 10 possible digits. Okay, which means we technically have 26 to the second power times 10 to the fourth, which I'll just go ahead and tell you what that is right now. That is 6,760,000 possible passwords. Now, here's the funny part. That's actually not that large. In fact, it's extremely insecure. Okay? Because the reality is the most effective password in the world is still technically 4 random words and 1 symbol. Because this can be brute forced by a program. Sequential-based data is so easy to break with a code. With a program, it's not even funny. That's why these next-gen passwords, why we have authenticators, because AI eventually is going to probably figure out how to break the four password symbol protocol, because it's going to be able to look at human behavior and one of the commonly most used words. Okay, so eventually, just like anything else, innovation meets innovation, and you have to keep innovating. Okay, now, and that concludes your notes. If you're at home, make sure you do your homework. Good luck.